Okay, everybody, welcome to our ninth lecture in ECE 576, Information Engineering. Just a quick announcement before we start. So in 2 weeks, your project mid-review is due. So that means you have to, I'm assuming you're making progress on your projects along the way. So there has to be a half-finished report that needs to be submitted on Canvas by it's November 16, I guess. So November 16, projects mid-review report. So there's no specific format. I think it should be half-baked version of your final report. So some things are missing, which is okay. You'll have time to complete it later. But the whole point is to make sure that you're on track and you are not stalling somewhere. So the report is ungraded, but I may ping you if you are unable to submit it, because that means that you are lagging in your project progress, and that's a red flag. So I just want to make sure that you're informed early instead of struggling at the final project stage. And remember, this is a significant portion of your grade, so take your projects seriously. We'll talk about it, I think, in before the Thanksgiving week, more about the project report expectations and the format. But then we will have the Thanksgiving week after that, after the mid-review, in which we will not have a lecture. And after that, you'll have like a couple of weeks to wrap up your reports. And if there's some suggestions, I will provide them to you via comments, and you can hopefully improve your projects by then. Okay, so today's lecture, we will continue our topic of data compression. And last time we saw symbol codes, mainly the Huffman encoders and the Shannon-Fano alias codes. So I'll give you a brief taxonomy here. Our data compression generally can be categorized into two broad categories. One of them is called the symbol codes, which we have already talked about. But there's another category which is called the stream codes. Symbol codes are basically codes where every symbol, right? Every symbol of the source is assigned a code word. Okay, and that code word is based on the frequency of occurrence. So if you recall, longer code words were assigned to symbols that were less frequent, and vice versa, to make sure that your length of the code is smaller, and hopefully you can achieve compression of the data. Okay, so now note that this requires you to have probabilities, or to know what really is the type of the source that is transmitting data. We saw last time that mainly symbol codes can be either Huffman codes, which is an optimal length encoder, but we also saw that there is something suboptimal, and that's called the Shannon-Fano alias codes. So today we are going to look at a completely different branch of codes, and that's called stream codes. And the difference here is that you kind of encode a stream of data, meaning you do the encoding on the fly. So you do not know what how the source emits symbols. So you are encoding a stream of bits on the fly. Okay, so as you receive the bits, you encode them. So it's not like a fixed encoder where you have a source stream and then you convert each symbol by symbol into the codes. So again, today we are going to look at two different types of stream codes. One will be called arithmetic codes. And the other will be called the Lempo zip codes. Okay, so let's briefly discuss what is the idea behind stream coding instead of symbol codes. So stream codes basically exploit the redundancy in data in a stream of data, right? So for example, if you are looking at English text, then by reading the first few sentences or first few words, you can actually predict the next word, right? So there's kind of linguistic characteristics that help you predict something. So it is that kind of predictability that we want to leverage in these type of codes. So what I will say is it exploits in a data sequence So for example, in a typical English text, we have we know that certain consecutive pairs of letters are more probable than others. Okay, and we also know that entire words can be predicted from a few letters. Given the context and semantic understanding. So if you understand the message behind the sentence or words, you can actually predict them by just having little information. So the first one of these stream codes is called the arithmetic codes. Let's take a look at more detailed view of what stream codes are like with this special category. And by the way, if you want to read about it, I will just put the book reference here because it's easier for you to take a look. So it's chapter 6 or 7 based on the edition of the book. By in McKay book. If you're reading that reference text, you can actually refer to this section for more detailed explanation on these codes, which may be a little complicated. Okay, so arithmetic codes, they are a special type of stream codes that assume there's an underlying probabilistic model that is generating the data. Or I would say, let's say there is a generating model for the data. Is available that supplies a predictive distribution of the possibilities occurring in the next symbol. So there's a predictive distribution of the next of the possibilities that may occur in the next symbol. Now the probabilities can be context dependent. So for example, in English text, you can have different possibilities. In other type of data, you may have different probabilities. So the probabilities can be depending on the context. So we'll take an example to see how we can actually convert probabilities or predictive probabilities into codes. So let me import some figures here. So for example, so this is an example for a uniform uniform kind of predictive probability. Now, maybe let's add a note here. So predictive are actually in the form of conditional density or conditional distribution. Right. So, for example, if I tell you the probability of x2 equals to A given x1 equals to A. Right, so that's a predictive probability. I mean, you know that x1 is already A, so what is the probability that x2 is also A? So for example, if you have a fair coin toss, or maybe continuous trials of a fair coin toss, can be encoded as follows. So, I mean, if you talk about a fair coin toss, then basically the conditional probabilities are the same as the probabilities of 0 and 1. Okay, so first thing is basically probability x equals to 0 is equals to probability x equals to 1, which is 0.5. And if I tell you probability x2 equals to 0 given x1 equals to 0, that's also 0.5. Okay, so similarly, similarly, the probability x2 equals to 1 given x1 equals to 0 is the same. And thing for the other given x1 equals 1 is 0.5, which is also the case when x2 equals to 1 given x1 equals to 1. So no matter how many times you repeat it, it's always going to give you zeros or 1 with the same probability, and which is equal 2.5. Now, if you want to encode that type of data, basically you will partition the 0 to 1 probability space into codes. So this thing here is telling you that the probability of x equals to 0 is 0.5. So you partition your half of the space so x1 is 0. This is telling you x1 is 1. And x1 denotes that the first trial value is 0 or 1. And then after that, we'll have x2, which is another independent trial, and so on. So if you do 2 trials, basically you will partition the space further. So you will have, so after 0, if you have 0, 1, then you are in this space, right? If you're 0, 0, you are in here. Okay. So now the example that this particular diagram gives you is the code 0, 1, 1, 0, 1. So from here, what I can tell you that you are actually in this region. So So the first one is 0. So that means you are in the top half. And the next one is 1. So you are in the bottom half of the first half. So you are in here. Okay, because of 0, 1. And then you get 1. So you are further here. Okay, and then you are 0. So you are in this space. And then you have another 1. So you are here. Okay, so it's like successively partitioning this probability space to a kind of developed code word. Okay, we will see another general example of how the codes are mapped to probabilities, or how the probabilities are actually converted to codes. So let's say, so here's a generic okay, where X or the stream, data stream, X1, X2, X3, and so on, right, can take values from or have so it's basically the probabilities. So so it's probability that from A1 up till AI. So the partitioning is as follows. So you partition the 0 to 1 space, which is here, according to the probabilities and the predictive probabilities. So essentially the idea is that so if a 0 has already occurred, that means that you get rid of this space here, right? And then the next the probabilities or the conditional probabilities you will have will basically partition the remaining space. So the same idea here. The first partitioning is when X1 can take value A1, A2, A3, and so on. Right, so if X equals to A1, we will have this piece here. And if X equals to A2, it's this space here. And then AI is here. So this is the first partition. But then when you look at the, let's say X is, the first one is A2. So you are in this region now. Now, if the next one is A1, the probability you will actually be in the top partition. But if the next one is A5, then you are in the last one. Right, so things like that. So your partitioning is actually successive, and so for example, if somebody asks me what's the code for A2, A1, it's going to be a binary conversion of of this probability here. And I'll show you that in the next chart. Okay, so let's see. So let's take an example here. So consider a biased coin with outcomes A, B, and this box that denotes end of experiment. Right, so we have a biased coin that has 3 possible outcomes. Now let's let the source string be B, 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 A, and then a box here. So let's say that's what's transmitted by the source. The probabilistic model, which you already know, of the source is given as, so you already have a probabilistic model of the source, which tells you the following information. So it gives you predictive probabilities. So it's going to tell you the source will transmit probability A with this probability, B with this, and this delta or a box with this. Now the next ones are interesting. So let's say if B has already occurred, then the probability of getting A is this much, B is this much, and dot is this. Similarly, if the sequence BB has occurred, then A, B, C have these probabilities, right? So given the context, which is here, these are the probabilities that you have. Now, using this information, you can actually draw a partition of the probability space and convert them into codes. So for example, if you look at BBBA, that's going to be this example here. So in this chart, basically, if you look at the probability space, it's partitioned into 3 pieces. So one is this, okay, which is the probability of A, and that's 0.425. So roughly 42.5% of the space between 0 and 1 you have allocated to A, and then the next one is B, which is about, again, 0.425, and the last one is 0.15, which is the box symbol. Okay, that's good. Now, the context tables tells you more about this. So if B has already occurred, then we are looking at this space. So if B has already occurred, then A will occur with 28%, B will occur with 57%, and box will occur with 15% probability. So you will partition it accordingly. So 28, 57. So out of this, this is 28%. Okay, this entire is 0.57, and then this is 0.15. So do you see this? So it's actually, maybe I will just say this is 28%. It's actually 0.28 times 0.425. So it's 15% off the 42.5%, which was already here. And then further, I mean, if you've already seen BB, then we have further probabilities. Right, so if you're in, so after B, you could have BA, BB, B square, but you were in BB. So after BB, you can have BBA, BBB, BB square. So information you have is about BBB, so you can further split this space into 3 pieces, and that's again according to the probabilities mentioned here. So essentially what is happening here is conversion of probabilities to codes. So if you have a sequence A, you will assign it a code word 0. If you have a B, you're going to assign it a code word which is, again, depends on the exact sequence. So so if you're looking at 3 bits or 3 input symbols, then you can just use 1 bit. But the more you go deeper, for example, if you're looking at BBB delta, so it's like four of them. So so it's going to tell you that you are actually in this space. So that starts with a so let's look at it in another way. So we're actually using 5 bits here. So so if you read it, basically at the root you have 0 and 1, but then that's partitioned into to further 0, 0, 0, 1, similarly 1, 0, and 1, 1. And this again is further split up. So essentially, this is just a standard division of the 0, 1 probability space into binary codes. So so I mean, let's look at this. So this one is the 0.5 line. Maybe the other figure has more clearly. Yeah, I can put this here. Yeah, so you see this. So this is the 0.5 line. So the top one is 0, the lower one is 1. Okay, and then you subdivide it into further sequences. Right, so 1 is further split up into 1, 0, 1, 1. Okay, now what this means is basically whatever is in this piece will start with 1, 1. and whatever is in the top piece will start with a 1, 0. And then so on. You keep splitting it up into 2 sections until you are until you have matched your the probability of the sequence. So in this case, if you look at BBBA, so you're going to be here. So you see, this is your BBA. But after that, you're looking at BBA delta. So you're already in this space where you are here. Or do you see this? So you are in this space between 1001 and 10011. So you want to read this point here in the binary code. So what I can see is you are after 10011. So this is your root, and then you have to further split this up, and that's zoomed in and shown to you here. So BBA delta is actually this code word. So my point is, you can have a sequence and then convert it into a code by reading off this table, and this table is standard. So for example, I can read you off some numbers here. So for example, the code for let's say AAAB is going to be 00011 and some more digits, right? That I cannot precisely read off from here, but I can see it is in this interval. Okay. So you're not going to be expected to do arithmetic coding in any of your homeworks or quizzes, but it's just an, I just want to give you a flavor of how arithmetic codes can actually be used to convert streams of data into actual codes. And the reason is complicated. You have to really zoom in and see the exact partition that you fall in. And that's not easy. Computers can do it, but doing by hand is harder. So now the last comment here is that decoding of arithmetic codes can also be done in a similar using probabilities from the predictor. Maybe I can just put a note here. you're not expected to do it on any of your assignments. Okay, now the next part of the lecture is on the second type of stream codes, that's called the Lempel zip coding. Okay, so this one is a it's actually a more practical type of compression scheme, and is actually used in real world compression standards. So it was actually introduced by Abraham Lempel. And Jacob Ziv, and that's where it gets its name as the Lempel-Ziv code, and it's a universal method for compression, which means it has a wide applicability and is widely used. So variants of Lempel-Ziv codes such as LZW, LZSS, LZMA are used in formats compressed file formats such as GIF or PNG or zip. And so these are commonly used formats, and it actually uses some variation of the Lempel-Ziv algorithm. And the method basically is, or the approach is to replace a substring with a pointer. To an earlier occurrence of the same substring. So essentially, if you have a long substring or long string, then sections of that string are actually may have already occurred before. So instead of rewriting the same substring again and again, you can just point it to an earlier occurrence. That saves you some space. Okay, so let's take an example to see how the Lempel-Ziv can actually work. It's a slightly complicated procedure, but hopefully you'll understand. So let's take a quick example here. Again, these type of codes are actually done using computers, so doing by hand is a little messy, but at least this algorithm you can understand with doing some hand examples. So assume a string or a source string 10 110 101 000 10 and so on. Okay, so that's the continuous string. Now find a LZ encoding. So that's your problem. Now, the first step in achieving this is actually to parse this string into substrings. Okay, so let's write the string as it is. So you have 1 0 1 1 0 1 1 and 1. So you have to basically split this up into substrings. So let's see how we can do that. So you take one bit at a time and see whether that string has occurred before or not. So for example, the simplest substring of this bigger string is just 1 bit. So let's put a partition here. So 1 is a substring of this string. Now, again, looking at the next one, 0 is again a substring which has not occurred before. So we'll parse it here. After that, we have 1. So 1 has occurred before. So we should look at a larger substring now. So instead, we will say 1 1 is a new substring, right? So it has to be distinct every time. So we will draw a line here. Now, after that, you look at 0. 0 has occurred before. So let's look at 0 1. 0 1 has not occurred before. So let's partition it here. After that, 0 has occurred. 0 1 has already occurred. So 0 1 0 is a new substring. The next one, 0 has occurred. 0 0 has not occurred. So this one will be a new substring. Then after that, 1 1 is a new substring. And in all this partitioning, we will just append a empty substring in the beginning, just for convenience. So we'll just call it lambda. This is actually an empty substring. Okay, so that's our step 1, and the results say that our substrings are lambda 1 0 1 0 1 1 0 1 0 1 0 0 0 and 1 1. So these are our substrings. Oh, I think I made a mistake here. So this one is 1 0. If you look at this thing here. So these are our substrings, and the second step is to write down the order in which the substrings occur. Step 2 says write down the order of occurrence of the substring. And let's call it S of n. Capital S of n. So in this case, so S of n is actually corresponding to the substring. You have to assign an order. So in this case, the lambda is at the 0th position, and so the order will be 0, 1, 2, 3, 4, 5, 6, 7. So that's the order, because we didn't interchange the substrings, so they are just all of them are in order. Lambda corresponds to a position of 0, and then 1, 2, 3 up till 7. So let's make a table of this information to help you find the eventual sequence. Now we will write a source substrings, then you will write the S of n, then S of n binary, then the last thing is the pointer, comma bit, that's going to encode the source string. So let's make a table here. Okay, so we have a 1, 2, 3, 4, 5. For our 7 substrings, the substrings are lambda, then we had 1, and then a 0, 1, 1, and 0, 1. Oh, I think we need more space here. Okay, so yeah, I think we are good now. So lambda 1, 0, and then we have the 1, 1, then 0, 1, 0, 1, 0. After that, we had a 0, 0, and then 1, 0. Now let's write down the S of n. S of n, as you recall, we just label them according to their order of occurrence. So this is 0, 1, 2, 3, 4, 5, 6, 7. Now S of n in binary is, because these are 8 of 8 values, so we need 3 binary bits, where this one is just 0, 0, 0. This is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. So that's the S of n in binary. Now comes the tricky part. So we have to create this pointer bit pairs for each of the substrings. So except the lambda. So we only need a pointer bit pair for these substrings, and that's your encoded sequence. So bit is simple because that's the last bit of every substring. So for example, in this one, this is really the bit in each case. So in this case, the bit is 0. In this case, the bit is 0, 0. In this case, the bit is 1. Okay. So that's the simple part. Now, important thing is the pointer. So what is the pointer? Pointer actually, so first of all, important to note that the pointer has a length which is actually the ceiling of log2 S of n bits. So if you look at the S of n and take the log2 and then the floor operation, the ceiling operation, then you figure out that actually pointer will be 3 bits for this. Then for these two, so remember log2 of 2 is 1. So we will have 1 bit here. So here pointer will be 2 bits. And in here, so pointer is going to be 1 bit of information. Now, pointer essentially is actually trying to point to this occurrence to a previous occurrence of this. So this this one has already occurred before, and that's the case here. So we can actually put a pointer to that instead of writing this one. So the pointer is actually this thing here. Maybe I will just point it out. this is the number that corresponds to 1. So we will write this pointer here. And that's 3-bit of pointer. Now for the next one, I will use another color, 0. And as for 0, 0 has also occurred before, and its pointer is this one. So we will just write a 0, 1, 0 here. And then to the other one, we are now faced with a 0, 1. And has 0, 1 occurred before? Yes, it has. And it has a S of n, which is 1, 0, 0. So we will have a 1, 0, 0 here. And similarly, for the next one, it's just going to be 0. So 0 has occurred before, and the sequence is purple one. 0, 1, 0. Oh, and by the way, we have to just use 2 bits now because the pointer should only be 2 bits. So it will be a 1, 0. And after that, we have to look at this guy here. And it has a binary pointer of 0, 0, 1, but we just use 2 bits, so it's 0, 1 in green color. And after that, we go and see what is here. This is the blank or empty empty sequence. So empty sequence has a 1-bit pointer of 0. So we will just put a 0 here. That's corresponding to this empty string. And the same one for the next one, but we don't want to, but that's the first substring, so we don't put anything here. Now, in conclusion, the encoded string is actually a concatenation of the pointer bit pairs. Okay, so in this case, it is, you start reading off from 1, so you will get a 1, 0, 0, 0, 1, 1, and then you have 1, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Okay. Okay, does anybody have a question at this point? I mean, I understand it's hard to follow. I mean, that's the reason doing it by hand is a little complex, but computers can do it, and eventually they do a lot of compression. That's how we see it in zip files and PNGs and GIFs. But important thing to note here is in this example, our encoded sequence is actually longer than the input sequence. So input was just this sequence, and the encoded one is a bit longer. So I just want to mention that in this simple case, encoding is longer than the source string And the reason why it is so is because there is no redundancy. Right? You see there's nothing being repeated over and over again. So we can't really get rid of any redundancy here. However, in a larger string of data, compression will generally occur. So if you've noticed, sometimes when you try to compress a file in WinZip or some zip software, sometimes it doesn't do anything, right? So its file length is roughly the same, and you're confused why you've not been able to compress it. The reason is that the data does not have redundancy. So you're not able to actually exploit that repeating sequences by using this pointer bit pairs. So I'm going to give you another example, and at least this example will show you that compression does occur when there is redundancy. So let's take encode the following. So if you didn't understand the procedure that we did earlier, I think this is another example that can help you traverse that process, and hopefully you can follow it when you take a look at your notes later on. So encode the following string using sample zip coding. Okay, now the string is 0, 0, 0, and then 3 zeros, 4 zeros, 0, 0, 1, 5 zeros, and then some more zeros. Okay, so as we said, substrings first, and then later on we look at the ordering, and then order in binary, and finally the pointer bit pairs. So let's write the substrings, then the SN, the S of n in binary, and then finally the pointer bit. Okay, so let's say we have a table, and first part was to find substrings. So let's start to parse this sequence, starting with the first bit. And so 0 is a substring, obviously. Then 0 cannot be a substring again, so 0, 0 will be the next one. And then we will have a 000 as a substring, and we will have 4 zeros as a substring. After that, again, 0, 0 cannot be one of them, so 0, 0, 1 will be. And now I think 5 zeros should be the next substring. And then the 6 zeros is the next substring. So that's great. Now, obviously, you see that there's a lot of redundancy here, and hopefully we can leverage that and use it to shorten our overall sequence. So let's get going. Our substrings will start off with the empty substring first. So that was a lambda, right? So maybe I can just write a lambda here. Then the next substring is 0. After that, we have 0, 0, then 000, then 4 zeros, then 0, 0, 1, then 5 zeros, and then we have 6 zeros. Okay, now the ordering is again straightforward. So we start with the order 0, 1, 2, 3, 4, 5, 6, and 7. And then we will convert them to binary, which is again also straightforward. So 0 will be 3 zeros, then 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Final thing is the pointer bit pairs. So let's write down the format. Okay. And again, I think it's important to highlight that pointer is 3 bits here. And the next one we will have is 2-bit, and for these is 1 bit long. So now first thing was just to copy down the last bits as it is. Right, so here's going to be 0, here's 0, here's 1, here's 0, 0, and a 0. Okay, now the next thing is the pointers to the remaining sequence. So there's this 5, 0 sequence here, which has already occurred. So that's the binary pointer. So we will just write 1, 1, 0 here. So next off, we are looking at sequence of 4 zeros, which has also occurred before. So that's a pointer of 1, 0, 0. After that, we have 0, 0, which has also occurred before, and that's the pointer of 0, 1, 0. Now the remaining ones will have, or remaining 2 will have pointer of 2 bits. So let's look at those. So the first one is 000. So we are looking at this piece, and 2-bit pointer will be 11. Okay, now the previous one is again 00 and 00 has occurred, but now you're looking at a 2-bit pointer, which is 10. And after that, we are looking at just this bit here, which has occurred, and we are only looking at 1-bit pointer. So we are taking this and putting it here. So perfect. We have found our encoding. So the encoded sequence is so it's a 0. So you just read off the pointer bit pairs. So 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0. Okay, hopefully I copied it correctly. So now the important thing to note is the length of the encoded sequence is 21 bits, which is down from 24 original source bits. Okay, so at least when there was redundancy, we were able to bring down our total number of bits used to encode the sequence. And when you're looking at larger files with thousands and thousands of source bits, you will actually achieve much shorter lengths, because obviously there will be a lot of redundancy. So I guess that was all for the encoding part, and primarily the whole target of today's lecture was to look at arithmetic and Lempel-Zev coding, which we have covered. I just want to go over the decoding part as well. So that's also another tricky thing here. So let's do this unit before we finish our discussion. Decoding is actually in a similar way, but we have to do it in reverse. So decoding so as a comment, basically to decode a Lempel-Zev encoded sequence, we need to fill up the table in reverse order. So that is, I mean, when I say reverse order, what you have to do is to fill the pointer bit pairs, and then introduce the substrings to get the original sequence. So let's take an example because it's easier to see it with the help of an example. So example where you have to decode the following sample zip encoded string. So it's a long string, which is 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, and then triple 0, 1, 1. Okay, let me just verify this again one more time. So I have 0, 0, 1, 0, 1, 0, triple 1, 0, 1, 1, 0, 0, 1, 0, 0, 1, triple 0, 1, 1, 0, 1, 0, 1, 0, 1. And then I have 4 zeros and 2 ones. Yeah, perfect. So again, we have the same kind of table that we have to construct, but we are going to fill it up backwards. So we'll see first the substring, and then the S of n binary, and then the pointer bit. Okay, so now I'm going to make a larger table. Probably doesn't fit in one line here, so let me just make 2 of them. Because I'm going to fill them up in continuity. So maybe just get rid of space here. Okay, so I'm going to do the first step again, which is the parsing step, parsing of the encoded sequence that, again, starting with the first bit, which is 0, and the next parsings will be at 0, 1, okay, and then at 0, 1, 0. And after that, we have a so, I mean, it's interesting because now so these are not source substrings that we are looking at, right? So these are pointer bit pairs. So, I mean, so the first one does not have a pointer to it. So 0 is the bit. So let me just. So if you remember, the first substring was always lambda, and then we had the source substrings here. So I'll just start writing down the pointer bit. So these parsings are not like the source string parsings. Now, so these are actually the bits. So I will just say the first one is obviously 0 here, right? And then there is nothing prior to it. But whatever next we pick, one of them has to be the pointer, then the other has to be the bit. So if I look at this one, basically 1 will go here, and the 0 is the pointer. So let's look at sequences or the orders. So orders always start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, things like this. So how many are these? So 0 to, yeah, maybe I will just add one more here, which is the empty substring, and that's lambda here. And this is 0, this is 1. Okay, so now if you write down the S of n in binary, it's going to be 0, 0, 0, 0, 0, 1. And then 1, 0, 0, 101, 1, 1, 0, 1, 1, 1. Then 8 will be 1, 0, 0, 0, 1, 0, 1, 0. Okay. So that's how it keeps going on. So if you look at the first output sequence, you can easily figure out that that's the bit piece, and the next one is going to come here, and 0 is going to follow. So let's put 0 here, This is this 0. Okay, that's how we came up with the output sequence. And remember, it's because for these pointer is one bit, okay? And then for the next 3, two-bit pointer, okay? And up to, so pointer is 2-bit up till here, right? So from onwards to 7, pointer is 3 bits. And here and then here. And then afterwards, you will draw a line at 4 bits. So 1, 2, 3, 4 here, and 4 here. Because that's the pointer for these. Okay, so on meaning that you look at 0th position, 1, 2, 3, 4, 5, and then for 6, again the pointer is 3 bits. The pointer is 3 bits, and then one more bit is going to be 4 bits, right? So this is 6, and then the moment you go to, 7 is also 4, and the moment you go to 8, 9, and 10, you will have 4 pointer bits, and 1 bit will make it 5 bits. So 1, 2, 3, 4, 5 bits. Okay, I guess that's the yeah, maybe it's the other way. So I should start from 1 here. For 1 and 2, you're actually looking at 1-bit pointer, and with the first one being empty, and then for 3, 4, you're looking at 2-bit pointers, and then 5 onto 7. You're looking at 3-bit pointers, which makes it 4. Actually, up till 8 also. 8 is what? Log 2 of 8 is 3. So it's 3 here, right? So this. So from 5 to 8, you are at 3-bit pointer, and then afterwards you are 4 bits. So that's what we have here. 4 and 4, yeah. So the last bit of each of these is actually the bit portion, right? So that we can copy directly, and the remaining is the pointer. So we did 0, 1, 0, 1 here, 0 here, and a 0 here, a 1 here, and a 0 here, and finally a 1. Now the pointers are actually these ones. So we will have 0, 1 here, 1, 1 here, 0, 1, 1 here. One, one triple zero, and 1 0 0, and then 1 1 0, and then 4 bits here, 0 1 0 1, triple 0 1. So that's the last one. Okay, now you've filled the pointer bits pieces. So the last step is really to fill up the substrings. So substring is easy. I think you just copy the bit pieces as it is, like the bit will automatically be the same. So the bit will be 0 here, 1 here, 0 1 0 0 0 1 0 and 1, and the substring will be whatever is the pointer. So look at the pointers. So for here, you don't have any pointer. So that's okay. So we look at the next one. Next one is pointing to 0. And the 0 is actually a empty substring. So that means you don't have any anything next to it. Okay. And then after that, we have 0 1 as the pointer. So 0 1 is pointing to 2. So sorry, 0 1 is actually pointing here. So maybe I will just highlight this. This is actually pointing to here. So we will pick this and put a 0 here. And the next one is 1 1, and 1 1 is actually pointing to this, which is now 0 0. So we will have a 0 0 here. Now the next pointer is 0 1 1. So that's a pointer to 0 0. So that's a pointer that makes it 0 0. And then after that, we have pointer as 0 1 0, which is pointing to just 1. So we will have a 1 0 here. The next one is pointing to 1 0 0, and that's 0 0 1. Next pointer is 1 1 0. That's pointing to 1 0. Next pointer is 0 1 0 1. So it's basically 1 0 1, right? So it's 0 0 0. Finally, we have 0 0 1. So 0 0 1 is actually 0. So we will just have 0 1 here. Okay, excellent. So now the source string is just a concatenation of all the substrings. So the source, so the original That is, you just start writing out the substrings together. So it will be 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 4 zeros, and then 0, 1. So again, I think if you start off from this source string and parse it, you will see that the parsings are correct and non-overlapping. And also, if you go the other way around, you can actually prove that the encoding is whatever we were given in the question. Yeah, so these are the parsings of the original source string, and if you encode it, you will get whatever we had in the question, which is this string. So not hard. You can actually and at least do some example, a small manageable example, maybe as part of your assignment. So in summary, I'll try to just briefly mention all the points that we have talked about today. What we have seen is stream codes, which are different from symbol codes that we were talking about earlier. And these encode data from a stream of bits. As it arrives. And the source symbols are not given a priori. So hopefully you realize the beauty of this, that for example, in the Lempel ziv coding, you don't know what is the source symbol is. You just parse the string and figure out what the substrings will be, and then you assign codes to them, and finally you try to get rid of the redundancy based on what substrings may have occurred before. So that's a really practical kind of scheme. It does not rely on any probability stuff. So obviously it's not optimal, but at least it helps you reduce the size of your files and your data. Now, arithmetic codes are one type of stream codes, and they are actually a kind of a hybrid scheme. So they bring you some elements of both stuff. So they combine a probabilistic model with an encoding algorithm that identifies each string with a subinterval of the 0 to 1 of size equal, so 0 to 1 interval of size equal to the probability of the sequence of occurrence. So every sequence has a probability of occurrence based on your predictor probabilities, and then those are mapped on the 0 to 1 interval. Now, the other type of stream codes, which we just saw, the Lempel-Ziv or LZ codes, are adaptive, as they memorize substrings that have already occurred. So no need to know the probability distribution of the source. Okay, and just a small note here that both both arithmetic codes and Lempel-Ziv codes will fail to decode correctly if any of the bits in the compressed file are altered. Okay, so you remember we studied error correction codes. That's a way to make sure we get rid of any alterations in the data. So compression is totally different and has a different purpose altogether. And hopefully, if no errors have occurred, I think compressions can be encoded and decoded perfectly. Wherever there is a chance of bits being altered, for example, when it goes through a wireless or communication channel, then we have to have error correction coding on top of it. So error correction coding actually prevents from the sequence prevents the sequence from alteration, and compression actually makes sure that you're presenting it in the shortest form possible. So their combination will make a efficient communication system. So that's the end of our first unit in this course, and that was the information theory part, where we studied different techniques and different parts of the wireless communication channel. It's not we haven't seen every bit of it, but at least we have had a flavor of the major components involved in the communication system. And each of these fields are actually a specialization in themselves. So there's coding theory that you can study to understand how codes are developed, and then there is this rate distortion theory and so many other things that you can actually go deeper into. But in this course, we've seen just an overview of the various elements of information theory and how they can be helpful in different parts of that communication system. So in our next, I'm just going to skim over the topics that are coming in the remaining lectures in this semester, which will be the second unit of the course. So it's more of inference than the information theory part. So at least for the next lecture, we are going to look at semantic networks. So when it comes to semantics, basically the important part is we want to incorporate context. So it's not only the data, but there is some meaning to it. So we are trying to give meaning to variables, and we treat the world as random, as random quantities. So everything in this world is random and happens with certain probability. So we really want to represent knowledge about a system as a graph. And then over that graph, we can study how information flows and how things are connected. So maybe I will just quickly mention a few facts. So we will introduce inference as a way to have knowledge of latent or hidden data based on observed data. So for example, if you had a variable x, right, or input data x that you transmitted, and then it became data y. So probability of y given x is the channel characterization, right? That's coming from the channel. If it's a binary symmetric channel, it's going to be something. But inference is actually the inverse problem. So inference is to find probability of x given y. That is what was initially sent based on what we receive. So therefore, inference is actually a reverse problem. And then we will see what are different graphical representations of these networks of information, and how we can analyze those graphs to obtain inferential information. So it's going to be a good few lectures before we can get there. So hopefully we are going to start that next week. And I guess we have 2 more lectures until Thanksgiving break. So
Sure.
yes.
How many more quizzes are we gonna have?
Okay, so next week there's homework, and then 1 more quiz before Thanksgiving. And after that, we have like another homework and another quiz. So 2 more quizzes, I would say.
Okay, because that would put it at 7 quizzes, right? So you said last week, I don't know if you
Yeah,
say you're gonna drop one of the quizzes if we go above 6 quizzes, that still remains the same or no?
yeah. So if we will have 7 quizzes, then I will just drop one,
Okay,
the
thank you, sir.
worst one for everybody.
Okay, thank you, sir.
Okay, any more questions? Okay, so wonderful. So you will have a homework uploaded this week, and that'll be due next week. And hopefully we will meet next week on Tuesday.
Professor, before you log off, can you scroll back up and just go through again how you were able to get the right here? Yeah, how you were able to get that initial substring.
Okay, now I started off with a encoded sequence, which is this long string. So these are actually pointer bit pairs. Am I right? So they are just, they are basically these things. Right, if I write them out together, they will be this encoded string. So I need to fill this table in a reverse manner. So what I did is I knew that it's a pointer bit pair. So for the first substring, we just have the pointer bit. We have the bit, we don't have the pointer. So I will just use this as that bit. The next one, I know that the pointer is 1 bit and the second one is the bit itself. So we have to pick 2. We have to pick 2 bits to put in there. So I picked the next 2 as the pointer bit pairs. After that, I know that the pointer is 2 bits and we have 1 bit here. So I have to pick 3 bits to fit in here. And that's for the next 2 boxes. So I picked 3 and 3 bits as parsings. After that, we have to pick 4 bits. And then the last 2 will have 5 bits. So that's what I did. So I picked 4, 4, 4, 4, and then 5 here.
I understand that part. I'm just really looking for you to go through the last step when you get, work back to the final step.
Okay, so hopefully if you understand how the pointer bit pairs are here,
Yes.
then the bits are actually the same as the last bit of the substring, right? So this 0 corresponds to this, 1 corresponds to this. This 0 is this 1 is this. This part you understand?
Yes.
Okay, wonderful. Now the next thing is the pointer. So pointer is actually pointing to a previous substring. So for example, here 0, 1, 1 is a pointer. And if you go back, look at the S of n in binary, this is where 0, 1, 1 is. And that actually represents the substring 0, 0. So I will just pick 0, 0 and put it here.
Okay.
Okay, so if you take any of them, so for example, this one, here the pointer is 1, 1, 0. So it's actually pointing to a previous substring 1, 1, 0. And that's here. So it's actually, the substring is 1, 0. So I picked this 1, 0 and I put it here next to my bit. Okay, is that clear?
Yes, that's clear. But what about the one next to with the SN of 9?
Okay, so this one, right?
Yes.
Have to look at 0, 1, 0, 1. So we don't have pointers of 4 bits which have 0 in the beginning. So we will just look at a 101. So this one. So essentially, the thing is, I didn't write it explicitly, but all of them have actually a 0 in the beginning. Do you see this?
Yes.
Yeah, I should have put zeros everywhere, but just to make it shorter, because that 0 is only relevant for the last two, the 9 and 10. So I just kind of skipped that and said, okay, 0, 1, 0, 1 is actually 101. So 101 is here, and we pick 3 zeros and put it here. Okay.
Okay, I understand now.
Yeah, ideally I should have put just 0 everywhere. Okay, perfect. So any other concerns?
No, that was it.
Okay, great. So, all right. So then let's meet next week, and I hope you have a great rest of your week. Okay, goodbye.
Bye, you too, Professor.